Here we have a beam, right? It's an overhang beam, and then we are trying to find the deflection, right? Deflection, which we usually write this way at the point B, right? But there's a new notation when it comes to this energy method or Castigliano second theorem method, which we write this way, right? So if you don't see this and you see this, you are the same thing. Okay, these two are the same. Okay. So then for this method, one thing that is clear is that we don't use a coordinate system. There is no clearly defined coordinate system. It just depends on you. You can move it any way you want, right? So coordinate system depends on you. Coordinate system depends on you. It's not clearly defined. Okay. The coordinate system is not clearly defined. The other thing is that the number of sectioning, that's very important. And the one thing I have noticed personally is that in order to find the number of sectioning, there's a way to do it. And then I'm going to do it right here. You check the loads or the reactions. So let's see, if you count the total number of loads, and let's say the loads are 5, right? You just subtract 1 from it, and then that gives you 4, right? This 4 here is the maximum number of sections that can be done, right? That's the maximum number of sections that can be done, the maximum. Okay, so let's go. Now we're going to count it, because that's the very basic, because if you're unable to do that, you won't be able to do the rest, right? And then one thing too is that, let's see, if you have a force, one force, we get to one force like this, and then let's see another force comes in, and then they meet at the beginning here. We don't count them, don't count it twice, just count it once, right? And then when it comes to the uniformly distributed, linearly distributed, we count their beginning and we count their end, right? Even for the linearly distributed, right, we count the beginning and we count the end, right, as 1 1. So let's use this example to get what I'm trying to talk about here. This is very important, because if you miss this, whatever it is that you are doing won't make sense. Okay, so now we are counting. Let's see, I'm trying to count the forces that we have here, right? So let's see, this is another one. That's very important. And then again, for this method, there's no clearly defined coordinate system. Okay, now we are counting. We have 1 here, right? And then we have 2 here, right? Because these two forces are meeting at this point here, so we count it as 1, right? So there's a reaction. We count reaction of force. This 1, this is 2, right? And then this is 3. This is another reaction, right? And this is the end of this force. This is 4, right? So we have a total of 4, right? When you add all the forces and reaction, you have 4. When you take 1 from this, right, that gives you what? 3. And then this 3 implies the maximum number of sections that can be done. The maximum number of sectionings. Okay, and then I'll draw some lines to actually show their positions on the beam. Okay, so let's see. Okay, this is very important. When you get this, whichever way the beam is, you'll be able to clearly define whatever it is that you have to find. Okay, so now let's see. Now that we know the maximum number of sections we must do, we must know their positions, right? Because it's not enough to know only the number of them, you must know their positions. When you know their positions, help you to get your condition, boundary conditions, and that way you'll be able to clearly find the deflection at that point, right? Oh, I've missed the annotations or the names of the symbols. So here's A, here's B, right? Here, somewhere here, it's like the midpoint of the whole thing. It's not a midpoint. It's not a midpoint, but it's C, right? There's D, and then there's E. And the question wants us to do what? Find the deflection at B, right? Which is how we write these. Now, concerning the position of the section, that's how it goes. Let's look at it very well. We know the number of sections we must do. We said that the sum of the forces and the reactions are 4, right? When they take 1 from this, it gives us 3. This 3 here is the maximum number of sections that we can do. The first one, and then we do the section between reactions stroke forces, right? So this one is here, this one is here. The first section will be about here. So let's label this I, right? What's the next one going to be? So we have this one here, this a force, right? This is a reaction, so the second one will be about here, right? What will the third one be? The third one will be between this reaction here and then this very end here, right? So 3, right? Okay, so the question is asking us to find the deflection at B, which is written this way, different notation but meaning the same thing, right? At B same as Y at B, right? Okay, so that's what we are doing. And then for the energy method, the Castigliano's second theorem method, what does is that whenever it asks you to find deflection, you must put a force, right, at the position where it's asking you to find it, right? And since the deflection, we are expecting it to come somewhere down, right? Yeah, so when you look at that, the position where it's asking you to do that, and then there's a force there in the same direction as how we want it to be, right? The same direction, we just go ahead and then we just remove the numerical value of it. We know it to be 34, but let's put it aside. Let's just cancel it out so it's clear. That's what we are using. Just take it out like this and represent it with P. You only get to replace it at the very end where you are trying to find everything, but now we are putting P there, right? So now we go ahead and then we try to find our reactional forces or our reactional loads, right? So that's how it to be. The reactional forces, reactional forces. Okay, so now we have AY here, right? And then we have a DY here. And then we have the other ones. We have the P, right? P, right? And then now, because we are doing forces, we're trying to change this uniform distributed load to a point load, right? And what we do is that we put it at just the center, right? So it's acting on the whole of this, right? When you put that together, it's about 22, right? So if it's here, so if let's say it's about here, right, and we are putting it at the center, meaning from here to here should be about 11, right? And then this right here is the 5 acting on the whole 22 is this, right? This is P, right? Now we're trying to find the reactional forces. So that's what we do. Sum of the forces in the y direction should be 0, and as such we get AY plus DY, right? These are the upper ones. We go to the downward ones, which is P, right, plus this 5 times 22, right? Yeah, because we've changed that one to a point loop. Now this is what we have. We can't find these unless we have another equation, 2 unknowns, so we need another equation. What's the next equation we need? Let's see. Okay, now we can take moment about any one of these ones so that we end up getting an equation in terms of just one of them. So we substitute and get the other, right? So let's say we take moment about, it can be any one of them, but just look at the one that's easier for you. So let's say you take the moment about A, right? Let's use it in this particular case. Moment about A, so moment about A should be 0, and as such, what do we do? Then let's put the distances on here. So the P is 10. Let's see, that'll be 10. This is 10 meters here, right? And then we know the D from here is 7 meters, right? And then we know that you have to get this 5 here is like 11, right? You can forget about it, you will find a way to do it later. So far as you know that one, you can do anything you want. So about A, right? So the first one we encounter when we are moving in this direction, right? That's what the P. So that's what we do. P is P, right? And the distance, we are picking this conversion to be this way to be a positive, right? You can pick anyone. Just pick the one that you can work with, or stay with the convention that you choose, right? So P, the distance is what, 10, right? And the next one is what? We encounter the 522, which is the force on its own. What's the distance? The distance is this whole length here minus the 11, right? So the whole length is 10 plus 2.5, this and then this. So let's see. This 10. This is 14, 25. This 10. 10. This 3. That makes it 15, 25. There's 33. Let's see. Okay. So just to make sure we're on the right path, that's how I'm doing this. Is it more appropriate to use a calculator? So we have a 10. Yeah, checking the whole length of the beam, right? And then we have a 2.5, and then we have a 12.5, and then we have 7, right? And when we add 7, right? 10, 2.5, 2.5, 7, right? Let's see. 10, 2.5, 2.5, 7, right? And now we are going back, so we take the 11 out. That gives us what, 21. So that's the distance of this one here from this side, right? Yeah. So this is 21. Which other force again? We have the D, right? And the D is in the opposite direction to what we've chosen. So that's a minus D. And the distance is what? From here to here. So the whole length minus 7, right? So that's about 32 minus 7, right? This time is not minus 11, minus just a 7. That gives us 25, right? 25 here. Oh. 25 minus D, 25. Oh. 25. Okay, let's move here. Okay, this is what we have. 21, right? And then minus dy 25. All this should be 0, right? Yeah, so now that we have this, we can make our dy the subject. Can make dy the subject. Okay. Dy the subject. By doing so, what do we have? We have dy to be equal to 10p, right? Plus 5 times 22 times 21, right? All this divided by what? 25. What do we end up getting? Let's see. 10 on 25. 5 goes to 2. 5 goes to 5p, right? 5, 22, 21. Let's see. So we have 2, 3, 1, 0. On 25. That's what we have. Let's see. Right, 25. That gives us 92.4, right? So our dy is 2 on 5 p plus 92.4. Natural says this should be force, so kilonewtons, right? To be precise. And now that we have this, we can go and then find our E, right? So let's see. We have this, we can find our A. So let's see. Okay. Now to find our A, our AY. Our AY now will be P plus 522, right? Minus all this, which is 2 on 5 P plus 92.4, right? It's 2.4. And our AY, then our AY will be, we have let's see, this is 1 minus 2 on 5. We are checking for the P. That gives us 3 on 5 P, and then we have 5 times 22, right, minus 92.4. That gives us 17.6, right, plus 17.6, and all this is all kilonewtons, right. We move on. So now that we have our reactional loads, we move on and do the free body diagrams, right. Let's go back. Our free body diagram, the first section we have here, which we've seen already, right. So let's move on. Let's see how that will be. Okay, free body diagram 1. So that's how it to be. Free body diagram 1. Okay, so it's this way. Sorry for that. Free body diagram 1. This. And when you're able to write on the actual diagram how it should be, you're able to follow up very easily, right. So it's good to even do it on it. So we know that our section starts from here and ends at where this green line is, right. So the only thing that we meet is just this reactional load at E, right. The reactional force at E, sorry, which we've now found. EY is Theorem 5 on 5P, right, plus 17.6, right. This is the only thing. Okay, so now that we have this moment over the points O is 0, right. So then we have M, right, being equal to this 3 on 5 P, right, plus 17.6, and the distance as well. This whole length of the first section is free body diagram 1, and it's safer to use, oh yeah, so it's I, right. So we see xi, right. So yeah, it's an xi, right. So now we have this, but then for this method, the deflection has a particular equation. The equation is of this sort that we see. You have to find the deflection, which is this, which is the same as this, right. It's actually integration from the lower limit to upper limit, right. And then we have the derivative with respect to, let's take it down. Let's take it down. Okay. So this is the actual thing. So the full equation for the deflection, the full equation is this: m derivative is partial respect to p, right, or not necessarily p, but the force that the load that you're putting at the position where you're trying to find the deflection, right, times m e I, right, dx, right. So meaning that whatever that you're going to do, you're going to need this portion, this, and then this, right. So when you, for each and every section that you do, right, for each and every free body diagram that you do, you should be able to find these two things, right. And at the end, we know how to go about it to find the rest, right. So now that we have this, let's actually file and write it out well. It's 5. Okay, so with this, we need two things, right. So we need a partial derivative of this with respect to p, right. So that's how to be. We end up getting 3 on 5 xi, right. And then the m, let's clean this. Okay, and then now to find the m, now we found this, we need the m, right. One thing about the m is that we Now to find the actual we have to find the value for p, right? And then when we look at the actual 10, this is what happens. Initially we said the force here was 34 kilonewtons, right? But then because you are looking for deflection at this point B here, right, replace the 34 because it's actually in the direction, right? And it's in the direction and at the position where we want the P to be, we replace it with P, right? So at that particular point in this particular case, we say our P is the 34 kilonewtons, right? So that's what we do. So there we say at B, right, this P is equal to 34 kilonewtons, right? 34 kilonewtons. P is equal to 34 kilonewtons, and we put it in the whole equation to get M because you need two things as we saw earlier. So then the M for the free body diagram 1 ends up being what? The P being replaced by 34, right? So let's see. In cases like this, I find it easier to use a calculator. It makes your work faster. Okay, so now we have it. Let's see. Okay, so the actual 10 was this. So let's see. So we have a 3 and 5 times a P. Let's make it X plus what? 17.6, right? And we have an X equal 34, right? So now we get our M to go 38, right? This is for the inside. We have an X1 outside, that's X1, right? For free body diagram 1. So we have the two things that we need as we saw earlier. So now we move on to free body diagram 2, right? So the free body diagram 2. Also, we've already looked at the number of free body diagram that we must do, right? Yeah. So now we know you have to go to what we did and see where the 2 will be, right? So the 2 is about here. So we encounter 1, 2, and about 3. Yeah, so 3 forces. So let's do that. Right, free body diagram 2 is how to be. You're moving from the left, and then you move from the position to make sure that you get the least number of forces possible, right? So we encounter this reactional force first, which is 3 on 5p plus what? 17.6, right? And then what do we have until we get to this I2 green line here? The next one we meet is the P, right? P. There's our P. And then looking at how the green line is, we get a part of the uniform distributed load, right? So then that's how we represent it. But then we know that before we get to the P, the distance is 10, right? So that's how we do it. See, from here to here is 10, right? And then there's a second free diagram, second section, x2, right? So there's a P, and then the uniform distributed load, we are trying to center it, so it's about here. But then we know that where the rest will be, this whole length here is going to be, so let's say from here to here, right? That length there is going to be x2 minus 10, right? But then because we are trying to center this uniform distributed load, this distance here, right, will be x2 minus 10 on 2, right? And then we have this 5 here, right? And then this 5, this is just a distance. This 5 is acting on the whole what? X2 times 10, right? Because we are changing the uniform distributed load to a point load, right? So that's what we have. And then because we've sectioned up to this point, different color, section up to that point over here, right? We have our shear, now we have our moment, right? So now we are taking the moment about O, right? We're saying everything about that one is 0. So we start with M, and we are moving this way. It's good to move that way. Check up and down to see which one you're encountering, right? The first one that you meet, let's see, the first one I will meet is in the direction of the m, so that's a plus, and that's the 5 something, x2 minus 10, right? This is the force itself. What's the distance? The distance is this, right, from this side, right, from the O here. Oh, it should be there, from the O, right? So that will be times this makes this squared, and then we have a 2 here, right? The next force that we encounter is the P, right? What's the distance for the P? It's actually from this side here, so that's x2 minus 10, right? x2 minus 10, right, for the P. What's the next one? Is this one. Let's see if we can move it here. Let's just put it down. So we have this one is in the opposite direction, so a minus, right? And then we have a 3 on 5p plus 17.6, and it's acting on the distance from the origin. This is the x2, right? So x2, we are seeing all this equal to 0. Now our aim is to make m the subject, right? See, when we make m the subject, we have minus 5, right, x2 minus 10 squared on 2, right? And then we have all minus p bracket x2 minus 10, right? And then we have a plus this 3 on 5 p plus 17.6 x2, right? And that's what we have. Then again, whenever you find the moment, you go ahead and find this, right? And then you find this at b, right? This is what we're going to do. And then finding this one, let's find this one first. So you are doing a partial derivative with respect to p. This one has, so we end up getting, let's see, this getting p to be, there's no p here, so everything here is 0. There's a p here, right? There's a p here, so we end up getting minus x, right? Yeah, so we have a minus x here, not just any x, minus x2, right, minus 10, because this whole thing is multiplying the p, right? And then what again? And come to this portion, we have a plus, right? So we end up getting 3 on 5 x2. So this is the only thing we have, right? So we are looking for m. So you are seeing that at b we have all p be equal to 34 kilonewtons, right? We make that subject, and our aim is to find the p, right? So let's see. Our aim is to find just the m at that point. Yeah, just the m. Put in the value for the p there. Okay. So to do that, this is what we get. Sorry for that. Let's see. Okay, we can see what we have. So this m here, again, minus 5 into bracket x2 minus 10 squared on 2. We have a p to be 34, so we get minus 34, right, x2, right, and then we get a plus 340, right? And then for the downside, that's 3 on 5, right, x, sorry for that, plus 17.6, right? So solve, and x is 34, and that gives us 38, right, for this whole thing. So we get plus 38 x2. And now we have this, we move on. You can even simplify. We end up getting m being equal to, let's see, minus 5 to bracket x2 minus 10 squared on 2, right? When I dealing with these guys, we end up getting a plus 4 x2 plus 340, right? So now we have what we need for the second free body diagram as well, right, for the second. So our aim right now is to move on to the third free body diagram, right, the third free body diagram, and see what we get for that one as well, right. So let's see. Then again, is your work becomes much more easier if you label everything on the original diagram, so you don't have to be thinking through everything all over again, right. So free body diagram 3, right. There's the thing. So now we use this to illustrate what I was saying earlier. Remember earlier I said something about because there's no coordinate system, we are not confined with where we choose our coordinate system to be, right. You can either move from here or move from this side, right. Okay, this is the reason why we say that, because you are not confined, you have the freedom. Okay, so imagine this. Let's see, what color should I use? We know definitely our third section is here, right. So if you try to section from this side, you do it this way, and then you get this, right. You get this reactional force here, you get this P here, you get something concerning the uniform distributed load, and then you get the, what's the name, the reactional load here. How many? About 4, right. But if you decide to use something from the right hand side, let's see how it will be. Much more simple, right. So like this. The only thing that you encounter is, because here is just a portion of the uniform distributed load. That's all. That is all, right. So it depends on you. Find a way to make your work easier. That's why we said, because you're not bounded by the coordinate system, you choose what you feel and you think will make your work easier, or your computation easier, right. I'm choosing on the right hand side. So that's what we have. We have let's see, this way, right, and then we do a section here, right. There's our O. Then again, when you section from the right hand side, your shear force goes up, right, and the moment is still in the same direction as usual, right. And then here, the only force that we're encountering is the uniform distributed load, right. Only the uniform distributed load. Let's see, let's go over it to confirm. Yeah, only the uniform distributed load, and it's actually acting on the entire thing. There's the third section. So let's see, this the whole length is x3, right. So if this x3, we know here to be 5, right, and it's acting on x3, so there's it. And then this distance here is all x3 on 2. Sorry, right. So this is what we have. So if we try to take the moment about O, let's say 0, we end up getting m being the same direction as that. So it's 5x, that's 3, right. This the force, and what's the distance? The distance is so x3 on 2. So we end up getting is in the same direction, so this should be negative. Yeah, negative. So m becomes minus 5x3 squared on 2, right. Then again we go over this partial derivative with respect to p. Since there's nothing here, this becomes 0, and then we need m, right. So then at b, right, you know p is equal to 34 kilonewtons, but then there's no p here, so m is still the same thing, minus 5 on 2 x3 squared, right. That's what we have. So we have everything we need, right, everything we need. The next thing is to just do the integration and then follow through the rest to find the deflection at b. Are we okay? One thing we should also notice is the interval. Without the interval, you won't be able to do the integration, right. So now let's look at it. When we look at the first section, which is this green line, is between where, because this one we started moving from this side, right. Looking at how even the section is done. Where is it? Right, this is how the section is done. So it started from this side, right. So this one, this x right here will be between 0, the interval between 0 and where, but that's the end, right. The next, where the next force is, right, which is about here, which is 10, right. So 0 and 10, 0 and 10. For the next one, right, the next section is between where this one ends, which is 10, and then where you meet the next force, which is here. So this is 10, and then what 10 plus these guys, this is 2.5, 12.5, that's 3, that's 15, right? So that would be between 10 and 25. Doesn't make sense. I'll go over it. Let's see. So the x here will be between 10 and 25. Sorry about that. The x here between 10 and 25, and this is y. Let's see. Okay, so it begins where this one ends, so 10, that's clear, right? But then where it ends is about here, so it must be 10 plus this 2.5, right, plus this 12.5. So this 12.5 plus 2.5, that's about 15. That gives us 25. That's why it's between 10 and 25, right? Yeah. So then the interval for the very last one, that one's very easy. Then again, this is what happens. Look at how we did it. We actually started from this side. You see, we section at the left hand side, right? So where did we start? We started from the right hand side. So we are just assuming that our coordinate system is about here, right? So that's between 0 and then since the next force that we encounter just after this green line is here, which is about 7, right? So between 0 and 7. And so that's how it is. 0 and 7, 0 and 7, right? So now that we have all these, just go ahead. A table is much more easier, makes your work is simple. So for the table we have 3 portions. A minute. 3 portions. Oh boy, sorry about that. Yeah, so 3 portions, right? Has the interval side. We have the M, the P, and then we have just the M, right? So that's all we have. The interval, right? And then we have this, right? And then we have this. The first interval was between 0 to 10, and this next one is about 10 to, what's the name, 10 to 25. Let's confirm that. So 10 and 25, yeah, 10 to 25, and the next one is the last one is 0 and 7, right? 0 and 7, 0 and 7. Now I'm going to put in their equations. So for the M, where's the M? Where's the MDP for this particular one? You have it to be 0 for the last one. This is it. This right here, 0, right? So that's 0. And this P, sorry, it's M, is minus 5 on 2, right? Minus 5 on 2 times x squared, right? So, alright. And the favor diagram 2, oh boy. Favor diagram 2, what is it? This 2, right? The M, so the MDP, where is it? This is it. Let's see, we can crop this out. Okay, we have it. Sorry. If you have it, can actually go straight for it. This is making my work long well. Just want to make sure we have everything we need. Let's see. Okay. So this, right? Right here. And then we have a changed minus x2 minus 10, right? Let's see. Minus x2 minus 10. Minus x2 minus 10. Sorry. Oh. This is getting messy. Let me just bring them down. Okay. So this is for the second one, right? Favor diagram 2. But it's very important that you're actually able to know this is for this is for that. That way, yeah, it makes your work easier. So this is what we have, yeah, and then plus theorem 5 x2. So let's see, plus theorem 5 x2 plus theorem 5 x2, and then the m for free body diagram 2, the m, we have it to be this or this. All negatives, everything is important. You miss a negative, you've changed the whole show. It's no longer what it used to be. So it's very important that you add the negatives and everything, right? Else everything will change. Okay, so let's see. Okay, so minute. This is taking longer. You can fast forward everything, don't worry. So far as you get a concept, you're fine. I'm trying to put everything here to make the work easier. So now we have this. Oh, minutes. Okay, and then this. Let's put everything down to see clearly what's happening. Okay, now let's see. Maybe we can take it there. Our table looks smaller though, but I'll use it that way. Okay, let's say this is for this one. Let's just put it here. Let's label it. This one is for this one, right? And then the interval 1, the dm, the p, partial derivative. We have it to be theorem 5 x1. So here's this one, right? And then what about m for the free body diagram 1? The m is 38 x1, right? Oh, it's taking long. It's getting boring. So we have everything we need. So the deflection itself is this way. This is what it says. Integration for the interval, right? A upper to lower to upper, right? And then we have partial derivative, right? It's equal to p times the m on ei, right? And then you have dx. Sorry about that. Should be dx, right? And because these ones are constant, we can definitely say that this should be equal to this a to b. Oh, sorry, I'm bringing the constant out. So that's 1 on ei, right, from a to b, and then we have this p times this m, and then dx, right? So yeah, that's it. But then because looking at how the whole thing is, we have more than one equations. What we basically do is that to get the m at the deflection at a particular point is this way. It's actually the sum of these integrations. Each and every one has their own limit, right? So that's the m, the p, right, and then the m, and then m, right, and the x, and then this ei here comes down here, right? Yeah, so that's how it is. So that's what I'm going to do. I'm going to find for each and every one of these the product of these two here, putting in the integral limit and everything, right? So let's see. The table, this ei. Sorry about that. So now let's see. This is how we need our calculator. Okay. Oh. Then again, you can just fast forward to where you want to look at. This is getting longer. Not my fault. Now we have this, and I'm going to do integrations, right? Definite integrals. So let's see. Definite integrals. Oh, it looks like I'm missing the integration. Okay, this. Okay. So now I need two functions, right? Two sides. I'm trying this one first. Let's see this. The first one, right? And it's from what 0 to 10. So alright. And then we have what Theorem 5 x, right? 5x. And what do we have here? 38 x, right? So when we do this, is I'll get 7600 for the first one. Let's bring it. Where should we put it? Okay, let's just put it here. This is 1, 2, and then 3. And these ones correspond to this 1, 2, and 3 here, right? So, and whatever we are doing here, we're actually multiplying these two and using this integral limit, right? So we have 7600 for the first one. Let's see for this next one. Another integration again. The limit is what 10 and 25. And what do we have here? Okay, you have, I'm multiplying two things. I do it this way to make my work easier. And I have a minus, I have another bracket. I have x, right? Minus 10, right? And then I have a plus. Okay. I have a plus here. Plus 3 on 5 x, right? And then what do I have here? I have it here. Oh, this is huge. Minus 5 on 2 on 2, another bracket. I'm doing it this way because I feel it makes my work easier. That's why I'm punching them this way, right? So let's see. We have x, right? Minus 10, and now this is squared, right? And then I have let's close this bracket. I have a plus, I have 4x, and then I have a plus 3 4t, right? That's it. So let's see. It's taking long. Yeah, that's it. Okay. Yeah, so that's giving me 13781, right? 0.25, right? And now the final one, because here everything will be to tend to 0, but let's do it for the sake of doing, to make sure we are clear on what we are doing. The interval is 0. Let's open this up. 0 here. What do we have? We have a 7. What do we have here? We're multiplying two things. Put a 0 here. The next one as well. Minus 5 on 2x, right? Squared. So let's see. This gives us 0, right? So this is 0 as well. So all that this ones, when we add these ones, right, that's what will give us this top side here, right? And then put the EI, right? The question actually gave us EI values, but it seems we've got them missing. But let's see. Right, so our deflection at B, let's use this. Our deflection at B, we've had the sum of that already, so that's 7600 plus 13781.25, 13,781.25. You're not in the 0. And then EI, right? The EI that was actually, I should have written this, my bad. The EI that was given in this question, we have EI. At times they might give them individually, but since in this case we are actually doing prismatic beams, that's uniform cross section, the value was given directly. So you have 37, right? 0.7 times 10 to the power 6. Right, it was I think kilonewton meter squared or so. I have to verify this unit, but this is the value that was given. Right, so 37.7 times 10 to the power 6. Right, definitely we know the unit for deflection, right? So that one shouldn't be a problem. You know, it's having the same unit as length, right? So it shouldn't be a problem. Yeah. So now that we have this, the next thing is just to punch this to see if we are doing the right thing. Let's see. Okay. Then again, you can fast forward to where you want to watch. Okay, let's see. Right. So no more integration. So we have a fraction. Oh. So we have 7600. 7600 plus 7600 plus 13 1378 1.25, right? All on 7.7 times 10 power 6, right? And this was given us. Let's see. And remember, because we were doing everything in meters, whatever it is that you point this will be in meters, right? So that's about 0.000567, and this will be in meters, right? In millimeters, it's about 0.567 millimeters, right? So let's see how that's it. We want 10 to the power minus 3, so we multiply by 10. Multiply by 10 power 3. Yeah. So this is what we have in millimeters. Everything in millimeters. Yeah, so that's it. Alright.